Good morning. So, what we're going to look at today is the start of that layer 3, which, as I said last time, is the protocol that pulls the internet. Now, we're just going to take a step back from the internet for a little while and talk about the cooperative routing. So today we're going to go through that. We're also going to look at distance vector routing. All the sound is wrong, so just give me a second. All right, I want you to think about routing purely as a problem of getting from A to B. Let's peel back all the technical terms. Let's peel back this idea of layers and things. When you're routing, you want to work out how to get from A to B. And there's lots of different measures about how to get from A to B. It could be cost, it could be distance, all of those sorts of things. So when we're routing, we're not generally just talking about one solution for everything. We're talking about how do we sort of optimize for some optimization traversing through the network. And if you think about your GPS in your car, you can choose green routing, you can choose fast routing, you can avoid toll roads, so all of those sorts of issues. Now obviously that's a lot more complex than the routing we're talking about at this layer, but still, there are lots of considerations. So when I talk about routing, what am I really talking about? What I'm trying to talk about is how do we get something from A to B? That's it. Now, it somewhat depends on what that something is. Cars, clearly that's different from eggs. But there's really two ways of doing this in our world, in our internet, in our networked world. The first way is treat your data in chunks. We've sort of seen this already because I've been talking a lot about packets. Well, the reason I'm talking a lot about packets is because there's an inherent bias in this course and all modern networking courses. And that is, data is in chunks. Okay, so that's our first model. Data is in chunks. The important thing about this is each chunk is sent independently. Think about, going back to some westerns you may have watched when you were younger, the idea of Pony Express. Okay, what happens is a man gets on a pony, he gets a satchel, it gets filled with mail, he then rides his horse somewhere and delivers the mail. Okay. Now the important thing about our Pony Express model is that each letter that you're sending over the Pony Express may go on a different pony and rider. And because they're going on a different rider and a different pony, they may go on a different route. So one rider may prefer a different route to another. And also, sometimes you had bandits, and the Pony Express was killed and the pony stolen, and so the mail didn't get through at all. But mail sent by another rider did get through, and maybe that was the second part of your message. So there's this idea of chunks where you've got this independence. Now, computer scientists like chunks, okay, because chunks are it's only a small piece of data, so we can handle it very simply. We can just deal with it one at a time. We don't have to have a big picture. So if we've got a chunk of data, we know what to do with it next. At least that's what the point of routing is. Problem solved. Now, telegraph. Okay, that replaced the Pony Express. It was wires strung on poles from A to B instead of people riding ponies. Now, what this actually meant was there was this idea of a physical connection between 2 points. You didn't have a horse and a man riding back and forth. You had signals going along a piece of wire that had a physical connection. So the other point is the connection exists for the entire length of that communication. Now, in the early telegraphs, they were all just a piece of wire from A to B. There was no switching. Later on, when people introduced telephones and things like that, exchanges, you started to see signals being switched between all these separate wires and joining them up. So, but nonetheless, that connection, even if we've got switches in the way, exists for the entire length of that conversation. Each bit of data follows the same route. And it's following the same route on a circuit, so everything arrives in order. That's quite different to our ponies. One pony could be faster than the other, so they arrive out of order. things like that. If your telegraph wire is broken, some bandits pull the pole over, for example, all data steps. So here we just lose our entire circuit. Up there we may have lost fragments, assuming we have enough ponies running it to all get through. Okay, so that's the basic premise. There's those two models. This idea of data in chunks and this idea of circuits. You can also think of this one as, no, I don't want to say that actually, that would just confuse you. Anyway, here's another, oh, I should tell you about this picture. This is 1861. It's a chap called Frank E. Webner, who was a Pony Express driver. And there are some telegraph poles being inserted. Now look, here the reading is sort of established hard. You know, people put the poles up on a particular route, and that's the route for all communications over those pieces of wire from then on and then forward. You can't just take a pole and move it somewhere else and have this communication continue. So anyway, there, if you like, is a physical hard way of establishing a route. Okay. What's this all got to do with computer science and computer software engineering and network engineering? Well, we're going to have to deal with those two different modes of communication. If we've got circuits, pieces of wire and stuff, we need to join them together to get from A to B, and there might be multiple pieces of wire and switches in between. Or if we're dealing with these individual chunks, these data packets, we have to work out when a data packet comes in, where to send it next. The difference between those two ideas, the circuit and the packet, is in when the routing decision is made. Okay? This is very important. The routing decision with a packet switched network is made when a packet arrives at the router. It doesn't matter what packets this router has been seen before. Even if it's seen packets from earlier in this communication, it doesn't matter. A packet arrives and the router says, oh hey, I know what to do with this, and it sends it on to the appropriate place. With circuit switching, the idea was the routing occurs before you send any messages, just like putting those telephone poles in the way. I mean, in the route. So before you send any data, you go through and you set up a circuit through all the routers or switches, and it establishes a circuit that's there for the length of the communication. So the routing is done before you even send any data with the circuit switch running. So you see those are two fundamentally different ways of handling this. One, oh, the packet's arrived, I'll send it there. And the second one, oh, I need to set up this communication, so I'm going, my router's going to connect to that router, and so on and so forth, and I'm now just going to relay everything through. So it's really that question of when those decisions are made. Packet switching at arrival time, circuit switching at setup. Very different. Now, both of these problems still involve having to decide which router or something to connect to which router, which piece of wire to which piece of wire, which packet to which router. So we have to do some path determination. That is, working out your route from source to destination. For this we use what are largely called routing algorithms. And of course we're going to concentrate on packet switching in this. Forwarding. This is the first function of a router. Basically, what a router does is it processes data from its input queue to its output. It's not a very exciting life, that's the name. And if we've got circuit switching, of course, as I said, you have to do the initial route setting for that. So here's a little tiny picture that you can probably hardly read of a router. You've got a selection of input ports, you've got a collection of output ports, and the point is to take things from here, switch through some fabric here into an appropriate output port. And of course, this is connected to some media, and this is connected to some media. So you want to switch through that. Now, the router includes a processor, so this is where it's starting to make some intelligent decisions, which controls the switch. Once you've made the decision, you want things through a switch to be made very quickly, because otherwise you get a loss of performance in your network. So you've got layer 1 here, layer 2 here, this is our layer 3 if you like, layer 2, layer 1. You've got some data link here, physical here, and our routing here. There can also be some special packets or control signals at layer 3, which to allow routers to coordinate and set each other up and things like that. So I want to point out that not just the data packets, if we're talking about a packet switch network, not just the data packets are flowing now, but also there's some special packets set aside for getting the routers to communicate and coordinate. And we're going to talk a bit about those in a bit. The switching fabric, as I said, just switches inputs. The routing processor maintains any tables that we have. Just like the switch, when you've got things coming on input ports and going out to output ports, here at the router, the next layer up, we've still got to make those decisions. And we keep that information in tables. Again, very similar to the switch you saw a few weeks ago, last week. But it's got a higher level of coordination. Because switches, you saw in layer 2 last week, don't talk to each other. Routers do. Routers have this little special club, and they get together and they decide how to send things. And they preferably do this in a distributed way and in a peer-based way. Okay, so routers are the next step up intelligence along with the next step up in state. These guys have a club and they get together to actually work out how to get things through the network. Okay, so before we talk about data switching, let's just do a little comparison here between Internet Protocol, or IP, TCP, IP, Internet Protocol, layer 3. This is the routing protocol of the Internet, and ATM. So ATM is a circuit switched protocol. It stands for asynchronous transfer mode. We're not going to do a lot about that in this course, but I'm going to have it here as a comparison. Now, this evolved from telephony, again, from those early telegraph ideas. And the point of these were to communicate human conversation. So human conversation has some interesting requirements. The first one is strict timing. If you're having a conversation with somebody, you expect a response within a certain amount of time, or you start talking again and then they talk and it's all confusing. So there are some strict timing requirements. Also, if your voice changes or something, I did that extremely badly, while you're talking, that isn't great for communication. So there's some strict timing and there's some strict reliability requirements. Do not spend the money, and if you lost the bit that said not, do spend the money. They're quite different messages. So you've got some reliability requirements there. So these basically combine for a need for guaranteed service. You don't need massive bandwidth, okay? You just need to make sure that most of the message gets through, and your ear, which is very tolerant, your ear can make up for a lot of errors. Your ear does all the error correction. The telephone system doesn't really have to do much. Your ear is quite smart. So there's this need for guaranteed service. Now, when we move from that telephone model to using this as a basis for data communication, these things take on an additional role where we have these high levels of service guarantees. Data must arrive in order, data must not have errors in it, data must arrive within certain timeframes, those sorts of things, once we start moving from human conversation to data. Okay, so the nice thing about this is you can have dumb-end systems. Okay, a basic telephone, I mean, look, not this is a smartphone, right? But 20, 30 years ago, telephones were really dumb. They had a microphone, they had a speaker, maybe this was 30 years ago, and 40 years ago. It's old history, right? And they had a dial, and all the dial then went back and forth. This caused electrical pulses at a particular coding to go down the wire, so the exchange would say, oh, hey, somebody's making a telephone call. I'll sort out my switches to put that circuit through. Now, similar things happen in the digital world, but back in those days, telephone was a really, really basic thing. And all of the complexity was meant to be hidden within the network. So your telecoms and stuff like that, they built these fancy exchanges that could recognize these pulses from these old rotary phones and then make the appropriate switches and do all of this stuff about guarantees and connections and stuff. So the idea here very much was the dumb-end systems. Everything difficult is hidden in the network. And that's true for ATM as well. The system doesn't have to worry. The thing that's connecting to an ATM system doesn't have to worry about anything. It sends bits in, it gets bits out. That's its job. Okay, all of the complexities in the network. Now, with the internet, we've got a packet switch system. Now, this is quite different. There are no circuits. Okay, it's elastic. Now, elastic can be good things or bad things, right? With cloud computing, you've got elastic computing, which means you can get lots of compute. Well, here we're talking about elastic not necessarily in a good sense. In this case, what we mean is, we probably should really describe it as a best effort service. Like the Pony Express, well, no, the Pony Express had some guarantees, you know. They did promise they'd deliver your mail, but they couldn't meet all of those if they got shot. But the point is here, there's no timing requirements. It's a best effort. Okay, I'll take the packet and I'll try to deliver it. That's the level of service we're talking about. Now remember, this is layer 3. We're going to talk about some layers later in this course, well, next week actually, where there are more guarantees added on. But here, at level 3, at the IP layer, the level 3 network devices have no pretense that they owe you anything. So if a router's sitting there routing packets from this input to that output, and it says, oh, actually, you know, I'm kind of busy, I'm kind of doing all the switching I can do in my routing function. So, you know that packet you just sent me, I'm just going to forget about it. I'm going to drop it. So there's no guarantees here. Routers drop packets all the time. Routers duplicate packets. There's all sorts of stuff going on. The smarts of this are not in the network. Routers are quite smart, but they're really just they're dedicated to switching packets and making right decisions about routing, not anything else. So all the smarts have to come from the end systems. So your computers, your smartphones and things like that. They have to deal with the rawness of the communication. Here, this was a high-level service. Here, your end system has to sort it out. Nice thing is, because it's ad hoc, it's elastic, it's best effort, there can be quite a lot of adaptation going on, quite a lot of performance controlling, packet filtering, all sorts of things like that, and a lot of complexity can be done. It's quite a free system, but anyway. There's many link types. They've got different characteristics, and you can't offer any sort of uniform service guarantees. All right. So I hope I made the point. The intelligence with ATM is in the network. The intelligence with the data packet switch networks is in the end systems. There's no guarantees with the packet switch system. It will just typically drop your stuff if it's too busy, whereas guarantees are inherent with a virtual circuit like ATM. All right, so this really is just a synopsis of what I've already gone on about. Sorry about that. You have to do route setup or call setup. So this is where I said the routers do it before the data flows, and of course it pulls it down afterwards. And the circuit through a whole pile of electronic switches and networks is called a virtual circuit. It's not a physical circuit, it's a virtual circuit. It's done digitally as well. Each packet carries what's called a VC identifier that describes, look, each packet. I should really differentiate this a bit better. When we're talking telephones and voice, it was one circuit. Now, what happened is, down on the circuit, you know, wires are an expensive commodity. You can't take a wire from everyone's house to everyone else's house. We know that doesn't work. So what in fact they did is they took the wire from the person's house and then they multiplexed it onto a bigger piece of copper. And so they shifted the frequencies. So each communication along that piece of wire would fit alongside the other. So that's called multiplexing. So you had, say, maybe 10 or 15 people having telephone calls simultaneously on a piece of wire. All right, that's fine, that's multiplex. Now, just because it originally started as an analog system like that doesn't mean the telephony system didn't get digitized. It got digitized very early. So it actually got re-implemented on top of a digital system, which looks like a packet switch system, okay? But you've still got to maintain all of these guarantees. So, right, that's the big button. So, the important things are, you've got to maintain those same guarantees that you've got from the telephone system. So the reality of a modern telephony system is you've still got packets flowing, but they're hidden behind, underneath the network complexity that's hidden by ATM, for example. So each packet carries a virtual circuit identifier that identifies what circuit this packet belongs to. It doesn't indicate where it's going because that's already been established in the setup. It just says, hey, I belong to this circuit. And so when the switches that operate between the various medias get this packet, they say, oh, you're on the circuit that got set up before, so I'll send you out there. It doesn't, and each packet in that communication takes the same packet. Okay? So all of those same guarantees are there, it's just, it's gone digital. Every router on the path of communication for a particular communication has to maintain the switching state about each connection. You can allocate buffers and bandwidth for virtual circuits to get higher levels of performance if required. All frames follow the same circuit. It's easier to manage. The routers and stuff handle congestion control, and in fact, in the setup phase, you don't set up a call unless you can manage the resources for it. If it goes down, it's quite difficult to recover the router. But here's an idea of virtual circuit routing. So we set up a virtual circuit here between Christchurch, Dunedin and Auckland, and it goes through switches in Christchurch and Wellington. Okay, so all packets follow the same route. All frames arrive in order. Before we could communicate any of those data, we had to set up that red link and store the state in each of these intermediate routers. Look, it says less resilient to errors, but you know this is part of the circuit's guarantee. They should be less frequent as well. And there's a certain amount of redundancy in here and a certain amount of reaction that these routers actually deal with. But from the user's point of view, when things fail, it's usually terminal. With the packet switch network, there are other options at the point. And because there are guarantees built into the system, because resources are allocated when you do the call setup, it's easier to achieve quality of service. So minimum guarantees as to bandwidth, jitter, and all of those sorts of things. Now, that was a connection-oriented protocol. The virtual circuit was set up. I'm taking a long time, so I should hurry. A packet switch network or a datagram network, this is your Pony Express one. Okay? I've said all of this. There's no setup cost. If a router fails, we can route around it. Nobody needs to notice. It's difficult to manage congestion because you're not going through separate routes, therefore you don't have an idea of how many resources are needed, and you can't really resource reservation to achieve that quality of service, which includes congestion. You can't really do it because there's no concept of resource reservation in the traditional IP packet. So, datagrams. We're going to call this datagrams from now on. We put data in things that look like telegrams, and we're going to send them into the network. All right. IP, the Internet Protocol. It's an end-to-end protocol that is source to destination. When we saw level 2 with the MAC addresses, that was link to link. IP is an end-to-end routing protocol. Every machine is identified by an IP address. IP datagrams are routed between machines over multiple hops in the network. So send, hop, router, hop, destination. It's a best effort model. Doesn't make any guarantees. I'll deliver it if I can. There's no sequencing guarantees. Things can arrive out of order. Things can arrive duplicated. Because remember how I talked about the switch? And I said the switch stores the packet in its buffer and then sends it out when the link is free. And I said that could cause duplicates. Well, routers do storing and forwarding as well. And it's a much greater problem. So you have to also worry about duplicated packets, as well as lost and all of those sorts of things. Now, most significantly, the IP protocol is hierarchical. So just by using the IP address, we can find the destination. And we'll talk more about that later. I want to really talk about the details of how to do a routing algorithm. Now, The main point here that I haven't really covered on this last slide here is this one. Routers don't have a global view. There's no circuit set up with datagram IP switching, data ping, IP datagrams. So all they know is who's connected to them and where they should send things next. So what happens is you get a packet in and you say, oh, I know about that, so I'll send it to the right place. Okay? The other one is, oh, I don't know about that. I don't know how to route to that IP address. So I'll send it to someone I think would. So that's really the two modes when you've got IP address. I'll obviously go into a lot more detail about that. So here's our good old Commodore PET. Here's another one. They want to communicate. Okay. So what we have instead is this multi-hop datagram network. These have 3 layers that we've already talked about. Physical layer, that's the piece of wire and encoding on it. Data link, okay, that's the point-to-point, and the network layer. This is the layer that connects all of these routers that deal with local areas together. So when we want to send this message from this Commodore PET to this Commodore PET, it does this. It goes up to the network layer. The router says, oh, hey, I know what to do with that. I send it to this router. So it goes down the stack, up the stack. This one receives it, makes the routing decision, and so on and so forth. Now, look, these aren't in a linear order. This could be a whole graph of these things connected in various places. But just for this particular route, we went through 3 routers, and each of those routers involved us going up and down the stack to layer 3. There are higher layers here that we'll talk about later in the course, but this is the fundamental. And this is called a hop. Between one router and another, it's typically called a hop. Okay. The thing to emphasize is this datagram routing is everything's set independently. So each packet follows its own route. So these are in 1, 2 in the sequence of a conversation. Packet 1 gets sent via Christchurch. Packet 2 gets sent via Wellington. And as you can see, different routes. If you have a route fail, you can just route around it. In fact, we saw that link between Christchurch and Wellington there fail. Okay. And we can just change our routing to accommodate that. There's no flow control either. Not in a diagram layer. So at layer 3, there's no idea of actually controlling how much data is flowing around. That happens at the next layer up, TCP layer. If at all. All right. When we've got multiple choices of path, is this thing even on? It's not charged for some reason. I have to keep bellowing. Sorry, I don't know what's going on with it. This thing is meant to charge it. Maybe it wasn't put in right. Okay, so as I said, look, when we route things, there's lots of, oh hey, it's picking me up now. If you don't hear it going, please let me know because I can't hear from down here. Unless it's really loud. See, now, it's okay. It's very loud. Okay. Right. See, the problem with these is you can't swear out your breath either. Okay, look, there are lots of ways we can make decisions. We can make them based on the things I sort of talked about. We can make them based on things like the shortest path. This is typically when we talk about hops. Routers introduce lots of delays in networks. So one of a really good metric for making a routing decision is what has the fewest hops, because each hop incurs quite a lot of network cost. We can also look for costs. Some links charge us money, and some links charge us different money. So we want to choose the minimum cost. And all of these sorts of things all these sorts of criteria we call costs. So when I say cost in the following examples, it doesn't actually mean money. It could mean hops. It could mean how busy the link is, all sorts of things. It doesn't really matter. All routes are built in a table, and they just use the I'm just going to show you an example because that sentence is stupid. There are lots. Okay, one thing I want to point out is I'm going to show you one particular routing algorithm. It's I think the easiest one to do in class. It's called distance vector. There are some real issues with it, and there are a pile of different algorithms that you can learn about in the 3D course. So I'm just going to take you through an example. I think this is the best way to deal with this. Now, this is a very simplistic view. I'm going to show you a slightly more formal algorithm in a bit. But this one is just to give you the really high-level idea. And this microphone is very sensitive today, and I can't hear it. Okay, so we've got this very simple network, A, B, C, and D. The lines obviously show the connections. It's not a fully connected network. Now, what happens is let's imagine this network all starts up at the same time. It's just been switched on with the flick of the switch. Each of these routers is going to have and build and maintain a table. Now, we don't want to go through, just like with switches, and program every single route in. That's annoying. We want these routers to be able to discover how the network's connected all by themselves. Nobody likes to do management, particularly network engineers, so let's let the network self-discover, just like switches do. So here's a typical table. We're just going to look at hops here, so we're not going to look at anything more abstract like cost. The next example we'll look at link cost. So here, that's one hop. From A to B is one hop. If A was communicating with D, it would be 2 hops. It's gone off again. I'm just going to blame the previous lecturers for not plugging it in properly. Okay, so it's back to bellow mode. Sorry about that. All right, so the first thing that happens is when you turn on your machine, it fills in its table. And guess what? You've just turned your router on. It knows nothing. Well, it knows one thing. It knows how to get to itself. Okay, this is routing table for A. Okay, if A is the destination, the next place you send it is A, and the cost is 0. You know what? You might think, oh, hey, that's really trivial, but it's quite important information. We'll see why in a bit. So every machine, every router that's turned on, whoops, went too far, that creates its initial table. It doesn't know, so D doesn't know about B, A doesn't know about B. Look, they know they've got some interfaces, but they don't know who's at the other end. So this is the stage where you actually discover that. So, now look, these don't have to happen in order, but let's just imagine all of these things do happen sort of at the same time, just for this example. So, what happens is that if the router's just started up, it's built its routing table, exhaustive as it is, and now it says, okay, I've got a routing table, I need to tell my buddies about it. I need to tell my other routers about it. So what it does is it takes this and it sends it in a special routing information packet down to each link. So that's the red box there, right? That's this routing table condensed into this red box. A has one as well, and so on and so forth. Now these get sent along the bits of wire, and remember each of these routers didn't know what was at the other end. And one from C arrives at A, one from B arrives at A. Now look, I've obviously only done a small number of the packets that can go, and one arrives at B from D. So those are the 3 packets, update packets that have come. Now, each one of those contained what the router knew. And if you remember, I'll just go back one. Each router only knew how to get to itself. So what you're sending down the link is, hey, this is how to get to me. Right? If you think about this is, you're sending to the unknown person or route machine at the other end of the link, this is how you can get to me. I'm at the other end of this. So what happens is A has received this packet from C. And C's thing just said, I can get to C the next place I go is C, and the cost is 0. So what happens is A can add that information to its table. A now knows that A can get to C, A can get to the destination C by following the link connected to C, and it costs 1. Right? Because look, it's just gone up 1 link. So it's all, every time you receive a routing packet, the cost to you is 1, is plus 1. Okay, so there's 1. Then B's packet comes along. B says it knows how to get to B, so we can add that to our table too. So, and again, hop cost 1. All right, now remember D sent a message to B containing D's equivalent of this. That then gets sent on via B. Sorry, I got ahead of myself. B updates its table and says, oh, hey, I've discovered a new route. I know now how to get to D. I better tell all my friends about it. So it sends that to A and to D as well. So there it goes. It arrives at A, and it says B knows how to get to D as well as B, and A says, oh, hey, I haven't seen D before, so it adds it to the table, and of course that cost plus 1, because we're counting in hops, gives us 2. So we've actually built a table. So now A router has discovered everything about this network. Now look, it might take more rounds than that to fully find the most efficient routes, but we're going to look at that in terms of the distance vector routing algorithm. Now, the nice things about distance vector is it's distributed. There's no high-level intelligence trying to decide that this particular route is optimal. That's really important when you're building network. Centralized things break, aren't connected, all sorts of problems. So every algorithm you want to be distributed and independent. It's iterative. So it doesn't find out the optimal network route straight away. Things can change, so it will change its routing tables. Over time, it will tend towards the most optimal route through a particular network, but it does so by little steps, iteratively. It's asynchronous. The routers aren't timed to communicate at particular times or rely on synchronization between them. They just, when they get some new information, they said, hey guys, look what I found. So there's no high-level synchronization. It's self-terminating. That is, once the network has been found and it's optimal, they'll stop sending packets, sort of. They'll stop sending lots of packets anyway. And it's all encoded in this distance table. Okay, so what we've got is we've got a table. We've got a row per destination. So those are our rows. And we've got a column per neighbor. So these columns define the physical links you've got. These destinations are the other nodes or other routers in the network. So I think the point to really stress here is this is a routing to router algorithm. So look, here's our example network. These just have some arbitrary numbers on here. These are cost, whatever that means. Okay, and so we've got a table here. This is A's table, and it's only got 2 links, one to B and one to C. So it's only got 2 columns. But we've got A, B, C, D, E, F as possible destinations. So it's going to have all of those as rows. So let's think about that initialization phase. What does it know? Well, actually, let's not get ahead of ourselves. The initialization phase is the next page. Okay, look. This is what the network would look like when we're all done from A's point of view. A can get to B via B for cost 2. A can also get to B via C for cost 7. A, C, so that's 1, 3, 3, that's 7. So you see all of the ones we have as all possibilities that we have physically connected. To get to C, we can go via B for 8, 2, 4, no, 2, 3, there we go, 2, 7, no, that's 9. Well, anyway, oh, there we are, 3, 3, 2, that's 8. So each of the routes that's possible is tabulated in here. So that's the end goal. I'm now going to take you through this algorithm to try and get to that. Now the point, one last thing is, we've got all of these. Which one do we choose? Well, of course we choose the minimum. So each of these rows, we just find the minimum number, and that's the best route. And look, we don't actually even have to know the whole route. We just need to know who to send it to next. We don't care that, for example, this one, we want to get to E, we go via B. We don't care what B does with it once we've sent it. We just know it's going to cost 6. The fact that B is then directly connected to E for 4 doesn't concern us. We just know that B advertises a route that it can get to E for the cost of 4, and our cost to B was 2, so that was 6. So we don't need to know what these links are doing with it from then on to get to C, to get to D, E, or F. We just need to know who to send it to next and rely on them to deal with the rest of the next hops. So that's the point, it's local knowledge. We've only got a horizon. A only has a horizon of this. Okay? A doesn't care what C or B do with it because it knows that these are the costs. It doesn't matter what the route is. Outside your local horizon. B's horizon, oh no, I'm not going to do that. Okay, so initialization. Okay, for each row, we set them to infinity. Okay, and then for each physical connection we've got, we put the cost in. So this is the initial table. B knows how to get to B for cost 2 because it's a direct connection. It doesn't know how to get to C via B, so that's infinity. Knows how to get to C via C, that's known cost as well. Via B, has no idea, that's infinity. Has no idea how to get to D, E, or F. All right, so I just want to go through this with you. Let's try and fill the table in for B. Okay. How does B gets to A?
B sees A directly.
Yep. Okay. B gets to A. What? I made a mistake. That should be B.
No, it's DB in the top.
Okay, sorry. Yes, sorry. Considering I wrote this morning, you'd think I had a clue, wouldn't you? Okay, so the table from B, it needs to get to A, it goes via A, cost 2. So what's the next line for C? Okay, B getting to C, there's no direct route, right? Oops, I went too much. Went too many. So it just fills in with infinities. D. Yep. E.
4.
Right. And F.
7.
Right. So we've done our initial routing table for B as well as A. Because the next phase is when you go and actually make a synopsis of this table and send it out to all your buddy routers. So this is A. So I've grayed out this part of the algorithm because we've done that already. That's the initialization phase. So now we're on this part of the algorithm, which is send it to all neighbor nodes once you've built your initial table. For each destination, so each one you're connected to, each of your physical connections. Okay. So let's have a look at A's example. We know about 2 and 1. So we create a small table. Those are our minimums, of course. So we create a small table saying, hey, A can get to B for cost 2 and C for cost 1. B is a much bigger example, but we find our minimums and we create this small table saying we can get to D for 3, we can get to E for 4, and we can get to F for 7. Now you'll notice in, I left A off. All right. It might make the next example slightly wrong. I don't think so. So what happens at A when it receives B's table? So we just saw on this slide here, A make its little table that's sent off to B and C, and B make its little table which it's sent off to A, E, F, and D. We're only going to care about A though. So there's A in its table, and it receives this table from A. A receives this table from B. A now updates this table. Now look, that A is missing. Okay? This is a shared link. It's not going to matter in this case. So what we do is we then update this table with this new information we've received. So D, well, we know this is from B, right? So we're going to update this column because that's the next hop, and we're going to put a 3 in there. And E, we're going to update this table, and we're going to put a 4 in there. And F, we're going to update this one and put a 7 in there. Plus the cost of this link. So B sent us this. It costs 2 to send on this link, so we're going to have to add 2 to each of those. So that's where we get the 5, the 6, and the 9. It's that basic cost plus the cost of this link. And we put them in the table. And we find the minimums. And we say, look, we've just updated our table, we're going to have to tell all our mates. So we built this table. B costs 2, C costs 1, D costs 5, E costs 6, F costs 9. And we're going to send that to everyone we connect. Now, let's imagine we got the packet from C first. C sent us D, 3, 6, sorry, not first. Now at A, we've received the packet at B. Oh God.
It's missing the B column. Yeah.
Yes. This is the trouble of getting up and deciding you've got a better way to do something, and you rewrite the slides immediately before. And you cut and paste it incorrectly. So, imagine this picture. I've got 2 minutes, it's not enough. Look, this should be the result from the previous slide, okay? Not this box, I should have cut and pasted the other box. Okay, from C we got 3, 6, and 7, and to our table you can't see here because I copied the wrong one, we update this and we can add a 4, a 7, and an 8 here. And of course we've got the cost of 1. So D plus 1 is 4, E plus 1, 6 plus 1 is 7, F, 7 plus 1 is 8, because those costs between C and A are 8. So please annotate your slides to show that I cut and pasted the wrong one. So now we've got more things to choose from, and we go through and we choose the minimums, and we're no longer choosing this route from A, and we're no longer choosing this route. We've now got a better route, which is this one and this one. So that's something new. We discovered something cool that we can tell everyone about. We've discovered some new, cheaper routes. So we create this, and we send it off to all our directly connected routers, which would be at C. Okay, obviously we've got to stop there. I'll pick that up next time. But the important thing is, all you're doing here is updating a table with costs and then finding a minimum. It's a very, very simple algorithm. And in fact, it's the one you'll be implementing in Lab 4. Using my 30 seconds I've got left. Lab 3 is out. It's basically do some experiments on the CNET simulator and write it up as a lab report. And then the next lab, you'll actually implement a better routing protocol than the ones you've got in that lab. Okay.